Hello to viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about radiocarbon dating. So let's dive right into it. Now first we have to understand this is not a desire kind of technology. This is something that we actually need because time is one of those things that erodes gods. It erodes civilization. Basically gods have come and went. That's how old time is. That's how powerful it is. It's not something that you and I can actually experience because we only live at best case scenario 150 years. I have not known anyone who has lived that long, but 100 is we can see that, and 150, let's say that's nothing compared to time. That's dude, that has way too many few zeros for comparison, so to say. And longest span of time, basically 1,000 year, 10,000 year, 50,000 year, makes human data useless, because while it is true that the modern human frame that you see, it is has been quote unquote finalized, so to say, in around 50,000 years ago. Of course you can take a 50,000 year old human, and now there will be some variation, some changes would be there, absolutely, but more or less it would be same. And in terms of civilization, we are finding older and older artifacts that are telling we may have sorted things out much earlier than we thought. So that creates an issue. It's we sorted things out and yet we lost it. So that creates an issue. There are many civilizations that has been lost to time. So it's how the heck this happened? What happened here? What happened to the people there? What happened to the language? All went poof. What the heck? And that's one of those things that we are old and nature works on a much different time span. For example, river is one of those things that if you grew up around a river, oh, that's a river that's gonna stay here. But here's the look at even 10,000 or 20,000 years, it's a river could be you know what, I don't feel like it, I can just go to a different place. Has happened. So it's one of those things that you have to understand. Us as a human, we have very small sight, and we really need our history to keep telling us it's bro, some things can change in much larger time scale, but does not mean it's not gonna change. Just because a river is static today does not mean it's gonna be static for next 10,000 years. It could just go poof. So this is one of those things that we need understanding of our time, basically thousands year, 10,000 year, 20,000 year. We need to know these things, and especially for humans also, it's what exactly calamity happened that poofed them out of existence. We need to know that. It's not optional knowledge, this is compulsory now. It's almost insurance level knowledge. So what about the tool? Now tool was created by William Libbey in 1949. Now this gentleman is a whole another level of amazing intellect. Basically American physical chemist, basically nuclear physicist you can call them. And because of the significance of the tool that he created, he has awarded a Nobel Prize. Let that sink in. That's this is serious. You may think carbon dating, that's not important. It's very important, very important. Now his brilliant idea was that cosmic ray is bombarding upper atmosphere. That's a known fact. We have done experiment, we have done tests, yeah, there are cosmic rays. Now here's the question, what happens to those? We know for a fact that atmosphere is stopping it, but what is, let's go poof, energy cannot be created or not destroyed. So what the heck is happening to them? Well, he figured out cosmic rays are converting, going through basically some changes and becoming neutrons. Basically you have electron, proton, neutrons. He's becoming that subatomic particle, neutrons. Now that neutron, because our atmosphere is majority nitrogen, it's reacting with basically nitrogen. Now nitrogen plus neutron creates basically 14C, meaning carbon 14 with one extra proton. Now that carbon 14 is reactive, so it reacts with oxygen and makes into carbon dioxide or carbon monoxide. So that creates a known source of carbon 14. Now we know carbon 14 has very short half-life, meaning 5,730 years plus minus 40 years. So that creates a ticking element, meaning a lot of energies are coming from the cosmic sphere that is being deposited in our atmosphere. That energy is being converted into C14, and it's not a permanent conversion. Basically, oh, it came, now we have C14. No, C14 will evaporate, not evaporate, basically change into different element after basically half of it will change after 5,730 years. That's a known thing. So that give him a light bulb moment. That means every living creature, meaning things that are part of carbon cycle, so to say, will have C14 as a fixed ratio, because our atmosphere is a quote unquote equilibrium, meaning the C14 that is coming from the outside, meaning cosmic sphere, it's locked. It's it's not randomly, it's okay, 50,000 ton extra was deposited. It's not. It's it's a fixed, lock limited, almost on a cosmic time scale, meaning for millions of years it has not changed. So all plants, meaning basically plants will consume that CO2, that fresh CO2 that was created from C14, and it's gonna go into its photosynthesis. That will create products. That products will be consumed by animals. That animals could be consumed by human, or human could directly consume the fruits, vegetables, vegetables and things of that nature. So we all have C14 in ourselves. Like if you keep hearing things like people say natural background radiation, like this is one of the primary element of that. Like C14, it's radioactive, it's everywhere. So it's one of those things that's like, okay, that means there is C14, we are detecting it, everything is awesome. Nature, every living creature and nature atmosphere itself is on equilibrium. However, the moment a living creature goes poof, dies, you have a scenario of inbuilt clock ticking, meaning that equilibrium amount, let's say it was X, it will no longer remain at X, because wait, time will start to flow, and because it's not alive, it's not consuming fresh C14, it will start to decay constantly. That creates a clock, inbuilt clock. At the point of death, it's locked. The end. Meaning any wood table, any cloth that is made out of cotton, anything that has been made through organic stuff will have a ticking element the moment of escape. So basically, your plant could be intact, but let's say the moment you took off its branches, that branches has locked carbon, meaning it's now having a basically C14, you can have assumed like, let's say X amount of C14, now it will keep getting X minus this much, X minus this much, X minus this much. So that's the tool that he figured out. Now what's the logic behind it? Well, logic is very simple. We are not looking for how much C14 is there. We are looking for the ratio between C14 and stable C12. Our atmosphere is flooded with carbon. Majority of them is C12. Now C12 is stable. Now it does have a half-life. Almost every element on the periodic table has a half-life, but it has a bit too many zeros to count. So it's one of those things like, yeah, from perspective, like comparative perspective, yeah, C14 is like, it barely lasts a few thousand years. So at death, C14 would be locked, meaning no fresh C14 can be introduced, meaning you cut the tree down, tree no longer had any method or any medium to absorb fresh C14, so it has locked, and half-life will start changing it. And that ratio of C14 to C12 will change every, basically let's say it had 100 ton tree. Just for lol sake, assume it had like 1 kilogram of C14. That means after 5,730 years, it will go from 1 kilogram of C14 to 500 gram, then to 250 grams, then half of that, then even half of that. So that's how you will keep figuring it out, like how far in time you are going. And it also gives off beta radiation, because C14 is inherently radioactive. If you have a good sensitive enough equipment, you can detect it using beta emissions, and that was like many labs use that as a measuring instrument. It's like how much radiation is giving out, and that will give you a good estimation of how much C14 is there, because that's how C14 quote unquote changes from one element to another. And even though we are talking about celestial sphere, there is a bit of difference in celestial sphere, meaning northern hemisphere and southern hemisphere are a bit different. Meaning if you have a sample, let's say a cloth sample, and you do not know which hemisphere it was originated in, you could have like really missed data points by like thousands of years. Not extreme, like it won't be like 10,000 year versus like 5,000 year. It will be like I think 1,000 or 2,000. You could be offset by that. So you need to know the origin place very reliably, quote unquote. You can't just randomly like, oh, I found something here, but let's say some old painting in India, people do that for paintings, because like some paintings that are very old, like 5,000 years or 6,000 years old, museums will pay a boatload of money. So they want to make sure that this is absolutely true. So they need to know origin of that painting. So just because it's found in India does not mean it has to be made in India. It could have been made in some other places, or same could go otherwise also. Let's say you found some old buried museum and it's like, oh no, this was not here, it was created somewhere in like, let's say Africa. You could find that scenario. So you need to know northern and southern hemisphere. Again, even without that data point, you will still have some idea, but sloppiness would be high. To have high precision, you need to know northern hemisphere or southern hemisphere. And there are a lot of calibration curve, like the people who are dealing with this sort of thing, they deal with that. I have provided a video down below exactly how these things are done step by step. Now you have to understand there are some serious limitations to this technology. For example, the starting amount of C14 is very less. I mean, like, how do we know? Well, we are not dead, because if too much C14 was there, it would be way too radioactive. So yeah, we are here, we are safe, we are alive. So that inherently means the C14 starting amount was very little, meaning anything that, like, for example, a tree, organic creature did not have too much C14. Like if it had like hundreds times more than that, of course, then we can trace it for much longer, but the starting amount was too little. That inherently means at 50,000 years, we reach a point where C14, there is still enough C14. Be mindful, there is quote unquote trace amount of C14, but it's too low. At that point in time, the output is no longer what you call reliable, scientifically accurate. People have tried to measure as far back as 100,000 years, and theoretically mathematically they should be accurate, but like that what we call measure confidence in the measurement is not there. That's why like people generally, like the moment it starts to show more than 50,000 here, they will try to figure out some other isotopes, they will try to use other elements, they will try to do some other type of dating. Carbon dating ends at 50,000, not because you physically cannot do it, just our instruments, our understanding, and our like the amount of precision. Like you have to go to almost background radiation level. So how the heck you know that you are detecting the C14 there, or C14 is coming from other sources or other contaminations? So it becomes very messy. But like at 100,000, yeah, at that point it's like no amount of C14 will survive. So it will like 1 or 2 atoms would be there. And it also does not work very good with non-living stuff, and that's why we will never hear people talking about carbon dating Apollo moon rocks, because it could have way too much C there, simply because it does not have atmosphere, so it has like direct bombardment. So how did that react? We do not know. So that's why you cannot use carbon dating on here, and we do not have like it's not living, so it did not have equilibrium. It was never in equilibrium. It could have like one spot got like bombarded by fresh asteroid, it's like it has very high C14, another place like nope, even though it's older. So that's why for non-living things generally people don't take carbon dating seriously. Now be mindful, non-living means in source non-living. So you will like people are carbon dating table, chair, cloths, things of that nature. There is a reason, because they had origin in organic point, it has that C14. That's why like our art industry is like very serious about this. Like many people have tried to like forge artworks, and that's how museums and library caught them. It's like the artwork is very good, how the heck you know that artwork is fake? You can't, because unless you have a time machine, or unless you have a photo of it going back to 15,000, like how would you know? Like of course there are some things, oh no, this is fake or that, but what if it's a rare equipment? You don't know. It's like, okay, let's just take a small part of that canvas or the cloth, ta-da, they know. So that's there are some limits for that. So what we can expect in the future, this is one of the things where our fossil fuel addiction is kind of creating a scenario where CO2 emissions is too goddamn high, meaning the fossil fuel does not have live C14, meaning for what are fossil fuel? It's also an organic product. It has carbon into it. However, because of its ludicrously long age, majority or almost 100% of the CO2, basically C14 it had turned to different things. So meaning it no longer has C14. So now we are burning it, pumping up into the atmosphere. We are changing the ratio from C14 to C12 is changing drastically. Now some scientists give a comical expression of that. It's like, think of it this way, like anything that is by 2050, if you take that and you give it to today, it's like, okay, 2050 element, give it today, we will find it like it's supposed to be thousands of years old, because that ratio has changed so much. Because we will find that C14 is too little, not because C14 is little, simply because C12 is too goddamn high. So that ratio has been changed. So that creates an issue. We cannot rely on basically carbon dating for the future. It's like, it's very awesome for us, but like for future, it's like, yeah, it's very sloppy, at best very sloppy. So it no longer has very high accuracy, meaning you must have second data source. Now people are looking into C13. Now C13 is also an isotope. However, it's a long-term stable isotope. Consequence is ludicrously rare. So how the heck you're gonna integrate C13 into the measurement? It's a bit more complicated, but people are looking into that because we have figured it out. And here's the ironic part, somebody figured this out in 1950s, that we are burning too many fossil fuels and it will change this ratio. I'm not joking. Like that's the scary part to me. It's like somebody figured out that early on. So this is one of those things that we are like, yeah, carbon dating for our future generation will not be as an easy tool as it was for us. For us, it's for like, we figured out carbon dating randomly. It's like, okay, this is the civilization, this is exactly what happened, this is when it happened, this is when there was a river, this is when this fish died. We cut everything. Like the amount of, basically we went from barely having some rough sketches of past to like a full 50 megapixel photo of the past. Like that's amazing. Like that changed a lot, including biology also, including evolution. Because yeah, evolution does stretch back millions of years, but if you can get a really stable picture for at least 50,000, like keep tracing everything for last year, that gives you much higher measuring confidence. So it was really important for. However, our future generation is gonna have some really hard time, and we are hoping that better instruments that that it's gonna detect the beta emission much more reliably, much more precisely, we should in principle be able to trace it out. And if we are available of able to archive our data properly for future generation, maybe they can get a trace curve with that. So using that trace curve, they will figure out, is like, okay, in northern hemisphere this is how much CO2 emission happened, in southern hemisphere this is how much CO2 emission happened. That's how, like, the C14 ratio changed. So utilizing that, we should be able to figure out some stuff. But that's for the future issue, to future generation to deal with thousands of years in the future, not right now. So this is one of the presentations that I've made guys for you guys. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.